We're good.
Okay. So, hi, everyone, and thanks for tuning in to this week's Quantum Chaos seminar. So it's my great pleasure to introduce today's guest, Nicole Yunger Halpern. She's an ITAMP postdoctoral fellow, jointly affiliated with both Harvard University and MIT. And before she started her postdoctoral fellowship, she did her PhD at Caltech. So in her research, she focused on updating thermodynamics using modern concepts from quantum information theory. And she's also been awarded various awards and fellowships throughout her academic career. So for the people who are tuning in for the first time this week, so during the talk, feel free to ask questions throughout the chat, and we really encourage you to do so. And also after the talk, there will be some time to ask questions. So again, introducing Nicole Yunger Halpern, who is going to talk to us about entropic uncertainty relations for quantum information scrambling. Over to you, Nicole.
Wonderful. Thanks very much to Pablo and Peter for the opportunity to speak here, and especially for holding this entire seminar series. I think it's a wonderful resource for the whole worldwide chaos community. And thanks everybody who has tuned in today. I'm going to share my screen now. I'm going to assume that you can see my screen, and in particular, the first slide of my talk. If you can't, then please feel free to let me know.
That works.
Great. So here's a very basic question about quantum theory. How much do two quantum operators, A and B, disagree with each other? And what does it mean for them to disagree with each other? You can ask this question of two different types of quantum physicists, and you'll get very different answers. First, suppose that you ask a pure quantum information theorist. This person may well say, put the operators in an uncertainty relation. If the uncertainty bound is high, then the operators disagree more. By the way, from now on, I'm not going to write any hats on top of operators. You can also ask someone who is probably, say, in the audience, someone at the intersection of condensed matter and high energy physics, someone who likes thinking about thermalization and black holes and ADS-CFT. This person will have the following setup in mind. We'll be thinking about an interacting quantum many-body system, such as a chain of a lot of qubits. Suppose that you inject some information locally with a small local perturbation. Maybe you flip one of the spins with some operator W. Then suppose that the system evolves in time. The systems that we're interested in here are interacting systems, especially systems that interact through non-local interactions. This evolves under unitary U. In the Heisenberg picture, this operator W will spread across the lattice, becoming W of T. It'll spread through many-body entanglement, so that later in time, no local probe V can recover the information that we initially injected. So in a sense, W of T and V disagree with each other. And we say that the information about W has scrambled. So we might, to connect with the question we just asked about what it means for two operators to disagree with each other, set A equal to W of T and V equal to B. And we can see that this second class of physicist would say that when information scrambles, W of T ceases to agree with V. Or A ceases to agree with B. So we have these two disagreeing operators, A and B, and the disagreement between the operators could lead to disagreement between physicists about what it means for operators to disagree. But we want peace on Earth, so we would like to be able to reconcile these two notions of operator disagreements, uncertainty relations and quantum information scrambling. Well, that was the goal of this paper. We proved an uncertainty relation for scrambling, in particular, an entropic uncertainty relation when cast in terms of entropies. We found that the uncertainty bound tightens when the system scrambles. So the uncertainty relation really does reflect the same sort of operator disagreement as signatures of scrambling. The key to this construction was a quasi-probability distribution, which is like a probability distribution, but it can exhibit non-classical behaviors. Probabilities are real and non-negative. Quasi-probabilities can be non-real, and their real components can go below zero. Here's where I'd like to go in the rest of this talk. First, I'll give some background about uncertainty relations, particularly uncertainty relations cast in terms of entropies, the modern version of uncertainty relations. Then I'll give more background and be more precise about quantum information scrambling. And we'll put the two together in an entropic uncertainty relation for quantum information scrambling. We can reason our way to its form via intuition. After that, the proof is not too difficult. We can see how it looks in numerical simulations of a spin chain and talk about opportunities opened up by this work. Let's start with more background about uncertainty relations. The old-fashioned uncertainty relations have the following form. They were first intuited by Werner Heisenberg early during the 20th century, and Robertson formalized the uncertainty relation that we know from our undergraduate quantum mechanics textbooks. A and B, again, are observables. This delta A is the standard deviation of A in some state psi. So suppose that you prepare a pure state psi, you measure the observable A, you'll receive some outcome little a with probability p sub A. Perform this process in a bunch of trials, and you can calculate the standard deviation. Over here on the right-hand side, we have a commutator of A with B evaluated in an expectation value. This uncertainty relation is very useful, is widely used, in particular to introduce students to the concept of uncertainty in classes, but it isn't ideal for a few reasons. One, the bound depends on a particular quantum state. It is in a large part the bound itself that quantifies the disagreement between the two operators. But if you choose the state in which to evaluate the bound to be one state or another state, then you can drastically change the bound. And it seems as though you have changed the disagreement properties or incompatibility of the two operators, but really all you did is change the state. We would prefer a bound that depends on the operators alone. Second, the uncertainty relation depends on the eigenvalues of A and B. The eigenvalues are basically labels on a dial. If we relabel the dial, then we're not really changing the system, we're not really changing the observables very significantly, but we can significantly change the standard deviations. So again, it seems as though by doing something very simple and not very physically important, just changing labels, we can drastically change the incompatibility properties of our operators. And that doesn't seem quite right. Finally, standard deviations do have very well-defined significances, but there are quantities that could be even more useful to have in an uncertainty relation. Uncertainty is very useful in information processing tasks in quantum information science, for example, in cryptography. Entropies are functions that are the workhorses of information theory. So it would be really useful if we could have an uncertainty relation that contained entropies. Hence, modern uncertainty relations, entropic uncertainty relations. The first canonical entropic uncertainty relation is the Massa and Oophink relation, which looks like this. On the left-hand side, we have these two H's defined as follows. Suppose that the observable A eigendecomposes like this, such that it has eigenvalues little a and eigenstates labeled A. Suppose that we prepare an arbitrary quantum state rho and we measure the observable A. We'll get some outcome little a with this probability p sub A. The Shannon entropy of that probability distribution is defined like this. It quantifies our average uncertainty about the outcome of the measurement. And as I said before, it is useful in information theory. Entropies tend to quantify the optimal efficiencies with which we can perform information processing tasks, such as data compression. We define the entropy of B analogously. So this left-hand side does depend on a state rho, but we will see shortly the right-hand side will not depend on a state, not depend on any states, and the uncertainty relation holds for all states rho on the left-hand side. The right-hand side depends essentially on C, which is called the maximum overlap. It's defined like this, and this definition has the following physical significance. Suppose that you prepare some eigenstate little b of the observable big B. and then you measure the observable A. You'll get some outcome little a with some probability. That's an inner product magnitude squared. Suppose that you do your best to guess the outcome of the big A measurement. This is your probability of guessing correctly, or your best probability of guessing correctly. Suppose that you can also choose your initial state little b in order to maximize your probability of guessing correctly. That is the significance of the maximum overlap. It is your best probability of guessing the outcome of an A measurement if you can measure any given or any desired B eigenstate. Again, the right-hand side of this relation does not depend on any quantum state as we desired. Let's see how this uncertainty relation works in a simple example. Suppose that our system of interest is a qubit, a quantum two-level system. Let the A observable be the Pauli Z operator. Let the B observable be the Pauli X operator. What's the maximum overlap? If you take any eigenstates of sigma x and take the inner product magnitude squared with any eigenstate of sigma z, you will always get 1/2. We say that the sigma x and sigma z eigenbases are mutually unbiased bases. This means that it doesn't matter which eigenstate of sigma z you prepare. If you measure sigma x, you will never have any idea whatsoever about what outcome we'll obtain. So the possible outcomes are totally unbiased. In this sense, quantum information theorists would say that the Pauli Z and Pauli X operators fail maximally to disagree. Because of that maximal disagreement, this maximum overlap is quite small. For comparison, suppose that both of our observables were sigma z. Then the maximum overlap would be 1, because if you prepare any sigma z eigenstates and you measure sigma z, you know exactly which outcome we'll obtain. And 1 is greater than 1/2. So this maximum overlap in the case of mutually unbiased bases is small, which means that the negative log of the maximum overlap is large. So the uncertainty bound is large, as we should expect for sigma z and sigma x, which we know don't agree with each other. What about the left-hand side? Suppose that we choose the state rho to put into the left-hand side that minimizes one of the entropies. For example, suppose that we choose a z eigenstate. Then we will set to 0 one of the entropies, but on the other hand, the other entropy will achieve its maximum possible value, log 2. So if you choose your state to minimize one entropy, the other entropy maximizes. So on the whole, the left-hand side is large as the right-hand side is. So the bound checks out. We've just seen entropic uncertainty relations. Now let's turn to the other notion of operator disagreement, quantum information scrambling. Again, here's our setup. We're interested in some quantum many-body system. If you're interested in high energy physics, it could be the boundary dual of a black hole. If you want to study how space-time might emerge from entanglement and the black hole information paradox, I find it easier to think about a chain of spins. So I'm going to focus on a chain of qubits. I'll label them from 1 to n. Our system is going to evolve under some Hamiltonian H. It couples the subsystems together. We're especially interested in non-local, non-interable Hamiltonians. That Hamiltonian generates a time evolution unitary that we'll call U. We're also interested in some state of our quantum many-body system that we'll call rho. Scrambling is defined in terms of local operators W and V. In some works, you'll find that they're Hermitian. In some works, you'll find that they're unitary. What I'm going to discuss, our results are general. They accommodate Hermitian W and V, they accommodate unitary W and V. But I'm going to, for illustrative purposes, keep in mind a simple example in which W and V are Hermitian and unitary, namely single qubit Paulis localized on opposite ends of the spin chain. For example, W could be the Z component of the first spin, and V could be the X component of the final spin. These two operators notably commute with each other. But again, in the Heisenberg picture, the W operator will spread to become a W of t. Its support will spread across the lattice until hitting the support of the V operator. And we say that information scrambles as the commutator grows. So I say the commutator, but really what we're more interested in is a commutator magnitude squared. As we'll see later, the commutator in this expectation value, not expectation value, but correlation function, the commutator itself would die off rather quickly because of cancellations between different phases. We want to ensure that there are no such cancellations so that we get significant measure that will stay at a non-trivial value for a long time, then we should take the magnitude squared of the commutator. So we have a commutator dagger times a commutator. So we have 2 terms times 2 terms, which gives us 4 terms. The most interesting term looks like this. It has a trace of W dagger of t, V dagger, W of t, V times our quantum state. That is called the out-of-time ordered correlator, which we have seen before in this seminar series. That has a horrible number of syllables, so I might sometimes say OTOC for short. It's often denoted by F of t. And in this notation, I'm replacing the trace with the quantum state with these angle brackets. We can see that this is a signature of scrambling and quantum chaos. In particular, the link to quantum chaos, I would be happy to explain during the question and answer session. We can easily see why this is called an out-of-time ordered correlator. Suppose that we start on the right-hand side of our trace and walk rightward along this x-axis, and along the y-axis, we plot the time parameter. So all the way on the right-hand side, we have this quantum state rho. It's not time evolved, so it's down at time 0. And we step leftward, we see this V operator. It's also not time evolved. But when we step leftward again, we get to a W of t, which is time evolved up here at time t. Step leftward again, we come to V dagger, which is not time evolved. Then we get to W dagger of t. This up and down motion is the reason for the name out of time ordered correlator. What does it do? How does it behave? Why is it interesting? Well, let's plot the real part of the out of time ordered correlator for some interesting system against time. The out of time ordered correlator will do something like this. For a while, it remains about constant. How come? At early times, W of t has not had much time to spread significantly across the lattice. So W of t nearly commutes with V dagger, in which case W dagger of t basically cancels with W of t to identity, and V dagger basically cancels with V. We're left with the trace of a quantum state, which is 1. So this out of time ordered correlator remains about 1 for a while. And by the way, the story I just told about this commutation and the cancellation to the identity, that in particular is in the case in which V and W are unitary in that illustrative example. Now, around here, there's a drastic change, and this is called the scrambling time. It's denoted by T star. By this point, W of t has spread across the lattice, and when we see this out of time ordered correlator drop, a member of this second community of physicists would say that means that W of t no longer agrees with V. So that's the measure used in this community. We might ask, well, why study such a complicated correlation function? Why not study simpler correlators like time-ordered correlators? We can measure these too. They will, in the cases in which we're really interested, say in cases of highly not-local couplings, decay reach their equilibrium values at a much earlier time and then about stay equilibrated. So if we measure just these simpler correlation functions, then we might think that no interesting physics happens at late times. The out-of-time ordered correlator shows us that it does. So that's a reason to study the out-of-time ordered correlator. This out-of-time ordered correlator reflects a late, subtle stage of quantum many-body equilibration, as well as quantum chaos, and scrambling, or the entanglement of many-body systems, and disagreement between operators. We've now seen two different notions of quantum operator disagreements, entropic uncertainty relations in pure quantum information theory, and out-of-time ordered correlators and quantum information scrambling in the intersection of condensed matter and high-energy physics. How do we reconcile these two notions? We might form the following guess. Suppose that you take that entropic uncertainty relation that we saw, and you replace A with W of T and B with V. Unfortunately, that strategy doesn't work because the resulting uncertainty relation doesn't reflect scrambling. It doesn't do anything interesting at the scrambling time. But we have a clue. So the entropic uncertainty relation that we saw replaced the Robertson uncertainty relation, which contains a commutator. And the out-of-time ordered correlator is the most interesting part of the magnitude squared of a commutator. So what if we took our entropic uncertainty relation and in some sense squared all the important parts of it? Maybe we could get the out-of-time ordered correlator, or sort of the essence of the out-of-time ordered correlator, and scrambling into it. What does it mean to square the components of the entropic uncertainty relation? Let's reason intuitively and physically. What about the left-hand side? Suppose that we replaced each single operator, A or B, with a product of two operators. Well, there are two operators that really characterize scrambling, W of T and V. So why don't we try replacing A with the product W of T times V? We need for A not to equal B, but we're left with just these two operators, W of T and V, that characterize scrambling. So let's try sort of time reversing the product and set B equal to, or replace B with V times W of T. It actually turns out that this is very much in the spirit of a semi-classical interpretation of the out-of-time ordered correlator in terms of chaos. I'd be happy to talk about that later if you're interested during the question and answer session. But there is a problem. This product of operators is not Hermitian. So how can we measure it? If we can't measure it, then we can't build up a probability distribution on which we will evaluate entropies. So what to make of this problem, we're not certain at the moment. But let's run with the idea for now. Later, we might be able to find a way to make sense of the idea of a measurement of a non-Hermitian product. That was the left-hand side. How do we sort of square the essential part, the right-hand side? The right-hand side depends essentially on the maximum overlap, which is a product of two inner products. Sort of squaring the right-hand side would mean turning C into a product of four inner products. It just so happens that such an object is known to characterize scrambling. And we can derive that object by decomposing the out-of-time ordered correlator in the following way. We said that the out-of-time ordered correlator equals the trace of W dagger of T, V dagger, W of T, V times the quantum state. The V is Hermitian and or unitary, so it has an eigenvalue decomposition. So we can write it in terms of its eigenvalues and eigenvectors. This is not the best notation because V is highly degenerate. In our favorite example, V is a Pauli operator acting on just one qubit in a huge chain. So V has only two eigenvalues, but it acts on a Hilbert space of dimensionality 2 to the n, where n is large. So it's very degenerate. It would be better to replace this outer product with the projector onto the little v eigenspace of the operator big V. Let me change my notation a little bit, just one more time. I'm going to label the eigenvalues V1. If V is a Pauli operator, then V1 equals +1 or -1. Similarly, we can eigendecompose V dagger. Now I'll call the eigenvalues V2 star. The star is here because of the dagger up here. We can eigendecompose the W of T, and we can eigendecompose the W dagger of T. Let's substitute in these eigenvalue decompositions, and then let's take the sums and the eigenvalues and pull them to the left-hand side of the trace using the trace's linearity. We'll find that the out-of-time ordered correlator equals a sum of some product of eigenvalues times a trace. That trace has 4 projectors in a quantum state. Now, we said that each projector is a generalization of an outer product. If we had instead simple outer products in here, then this trace would be a product of 4 inner products. So what we have here is a generalization of a product of 4 inner products, which is exactly what we were looking for on the last slide. So we have this trace thing, but what is it? It looks really bizarre. It turns out to be a quasi-probability. Let's review quasi-probabilities. Quasi-probabilities are often used in quantum optics, but more recently, they've been very important in the foundations of quantum theory and in quantum computation. These are the quantum versions of phase-space densities in classical statistical mechanics. Suppose that you have a set of classical particles and you want to describe their state. You will draw these axes in phase space representing, say, positions and momenta, and you'll write down a phase-space density, a probability distribution over phase space. You might wonder whether you can represent quantum systems the same way. We almost can, but we have to give up at least one axiom of probability theory. Probabilities are real, they're non-negative, they're normalized to 1, and they compose in certain ways. Relaxing different axioms leads to different quasi-probability representations of a quantum state. By representation, I mean a function of, say, some q and some p, such that from this representation, we can calculate expectation values and probabilities, what we like to calculate using quantum mechanics. The most famous example is the Wigner function, which probably a lot of people in the seminar have used. The Wigner function famously goes negative. Under certain special conditions, the negativity can signal non-classical physics. This trace here I call the quasi-probability behind the out-of-time ordered correlator. It was first discovered in this paper, and this paper here is a sort of biography of the quasi-probability behind the out-of-time ordered correlator. What do I mean by quasi-probability? Suppose that we marginalize over every index except for 1. So we take our trace here, and we marginalize over all of the eigenvalues except for 1. So we marginalize over V1, W1, and V2. We're left with a trace of the projector onto the W2 eigenspace times rho, which is a probability. So if you take a quasi-probability and marginalize, you get a real probability that's normalized to 1. This quasi-probability can assume negative and non-real values. So relative to the Wigner function, it has an extra degree of freedom. This turns out to be, if you look back many decades, an extension of the Kirkwood-Dirac quasi-probability. So Kirkwood discovered in 1933 and Dirac discovered in 1945 a quasi-probability distribution that, if generalized, has an instance this. There are a whole bunch of references in this biography paper. This, frankly, is my all-time favorite quasi-probability distribution. So I really encourage you to look into the Kirkwood-Dirac quasi-probability. It is, at the moment, it has, let's say, recently not been very well known, but over the past few years, it has undergone a huge renaissance, as I will show shortly. So now we can understand the decomposition that we arrived at a few slides ago. We said that the out-of-time ordered correlator equals this sum over this eigenvalue product times this trace. Now we can see that that means that the out-of-time ordered correlator is nothing but an average over a quasi-probability distribution. The quasi-probability distribution contains all of the information in the out-of-time ordered correlator plus more information, because the out-of-time ordered correlator is just one coarse grained number. This quasi-probability distribution is a whole list of numbers, so it contains more information. This quasi-probability distribution has turned out to be far, far more fruitful than I ever imagined. So here's a bunch of literature about the out-of-time ordered correlator quasi-probability. The out-of-time ordered correlator motivated this generalization of the Kirkwood-Dirac quasi-probability distribution, which has now found applications in metrology and foundations of quantum mechanics. People have measured this distribution recently in experiments. There's a whole lot of work being done on this quasi-probability distribution, and it turns out to be really essential to scrambling. So I really encourage people to look into it. Now, one useful property of this quasi-probability distribution is that it can be measured experimentally with weak measurements, which don't disturb the measured system much. What's a weak measurement? Well, what is a quantum measurement? We have our system of interest, we have our detector, and we couple the two together, then we project the detector. From the outcome, we infer something about the system of interest. We usually assume that this correlation is maximally strong, so that the two systems are maximally entangled. But we could make the correlation weak, associated with an energy scale lower than the intrinsic energy scale of either subsystem. Then, when we project the detector, we can't infer very much about the system of interest. You might ask, why would we want to give up information about the system of interest? Because we don't disturb it much, and a lack of disturbance can be valuable in quantum theory. Plus, if we perform a whole lot of trials, then we can recover the same statistics that we would if we performed strong measurements. Let's parameterize the weak coupling with a weak coupling constant G. We can, I mentioned that recently this technique has been used in experiments. This isn't my favorite phrasing, but some people say that you can use weak measurements in order to sort of measure non-Hermitian operator products, as you would measure, or similarly to how you would measure Hermitian operators. It turns out that you can measure something that looks a lot like an expectation value. Just inside, you don't have one Hermitian operator, you have a non-Hermitian product of operators. You can do that using weak measurements, and I'll give a little more detail about how. This should give us an idea, because we said that it would sort of make sense to put into our entropic uncertainty relation non-Hermitian products of operators. But we were stumped because we didn't know how to measure them, and so to recover statistics on which we could evaluate entropies. Now we know we can measure these using weak measurements. So where have we come to using this physical reasoning? We should conjecture the following. We can reconcile uncertainty relations with quantum information scrambling by proving an uncertainty relation that looks like, sort of like this. So we take the entropic uncertainty relation we know. We replace A with the product W of T times V. We replace B with the reverse. And the way that we would measure these entropies involves weak measurements. And then this maximum overlap will come to contain the quasi-probability behind the out-of-time ordered correlator. This is generalization of a product of 4 inner products. And that contains all of the information that the out-of-time ordered correlator contains. So it knows when the system scrambles, and it can tighten the uncertainty bound around the scrambling time so that the uncertainty relation will reflect the same operator disagreement as the out-of-time ordered correlator. Can we prove this conjecture and make it precise and sharp? Yes, of course, that's why I'm giving this talk. Here's a sketch of the proof. First, we need to find a generalized entropic uncertainty relation. I showed you an entropic uncertainty relation that involves just projective measurements of Hermitian operators. There are other types of measurements that we can make. In quantum theory, we represent generalized measurements with positive operator valued measures, or POVMs. Entropic uncertainty relations for generalized measurements have been proved. So we take these abstract uncertainty relations out of the literature, and then we find the right measurements on which to evaluate them so that we'll end up with an entropic uncertainty relation that reflects scrambling. It turns out that the right measurements to choose are the following. First, one measurement consists of a weak measurement of V, followed by a strong measurement of W of T, so a sequence of measurements that forms an effective measurement. And the other measurement consists of the reverse process. Then we take these measurements and we substitute into the right-hand side, so we calculate the maximum overlap C. Unfortunately, the result is not necessarily experimentally accessible, it's just some piece of math. But we can take this log and bound it in terms of quantities that we know how to measure experimentally. The tools that we use are Taylor approximation in the weak coupling constant, and the monotonicity of the Schatten p-norm. Not very important details. So we end up with the following entropic uncertainty relation for quantum information scrambling, which has this form. On the left-hand side, we have our sum of entropies with the two measurements that we chose. In the bound, we have a largest term that is proportional to the coupling constant, and that multiplies a classical factor. Basically, it doesn't tell us anything about scrambling. It depends on just probabilities, classical probabilities that are real and non-negative. But there's a term proportional to the coupling squared that contains the out-of-time ordered correlator quasi-probability. And then there are higher order terms. But this G squared term changes at the scrambling time, enabling the uncertainty bound to strengthen, to reflect scrambling as we wanted. And it does make sense that this scrambling factor is part of a small term, because as we said before, the out-of-time order correlator itself is a 4-point function. That is quite high order. That's very subtle. So it makes sense that the effect of scrambling on this uncertainty relation is subtle, is high order. What does the uncertainty relation look like? To find out, we simulated a chain of 8 qubits. We used the power law quantum easing model to generate our evolution. The power law quantum easing model involves an easing coupling, a ZZ coupling between each pair of spins, and the strength of the coupling declines as a power law with the distance between the spins we're talking about. We also added transverse and longitudinal fields and chose the parameters such that the Hamiltonian is non-integrable. We also checked what happened in the integrable case, but that's less interesting. We chose for our out-of-time ordered correlator to have a V and a W equal to Z components of Pauli operators located on opposite ends of the spin chain. But this choice doesn't matter very much for non-integrable systems. So bound looks like this. Let's focus on this green line. Along the x-axis, I've plotted the time, and along the y-axis, we can see various terms in the bound. Something dramatic happens at around t equals 4. You can also plot the out-of-time ordered correlator for this system, and you would find that this is the time when the out-of-time ordered correlator drops. So this is the scrambling time. And the green line represents the sum, so the bound on the right-hand side of our entropic uncertainty relation. At the scrambling time, it ticks upward, so it strengthens. The bound strengthens at the scrambling time, so we have an entropic uncertainty relation that can reflect the same quantum operator disagreement as that underlies information scrambling. So we have reconciled the two notions of quantum operator disagreements. What can we do with this? First, we can check this uncertainty relation in experiments. We know how to measure the quasi-probability distribution behind the out-of-time ordered correlator, as I mentioned, using weak measurements. Also, recently, there was a paper that generalized this scheme so that you can, if you're using qubits, just use strong measurements and perform some extra measurements as well in order to recover the quasi-probability. This scheme is amenable to a wide variety of platforms, especially superconducting qubits. The technology has advanced so that both the couplings that we would want to create an interesting scrambling system and the ability to perform a sequence of weak measurements are basically in place. A very simple version of this test has been performed recently. So you could take this entropic uncertainty relation for quantum information scrambling and simplify it a lot. You could get rid of the scrambling. You could even get rid of the many-body nature of the system. You're essentially left with an uncertainty relation for strong and weak measurements. This uncertainty relation was recently tested and explored thoroughly in the lab of Kader Murch at Washington University in St. Louis. Kader has superconducting qubits, and the paper on this simplified entropic uncertainty relation will come out later this month. But again, the full problem that involves scrambling is still open. Also, the quasi-probability, as I mentioned, can exhibit non-classical behaviors by going negative and non-real, exhibiting behaviors that can't be exhibited by classical probabilities. Also, an uncertainty relation reflects non-classicality and has its own type of non-classicality. If an uncertainty bound is non-trivial, then we have some non-commutation. It'd be interesting to find out whether one sort of non-classicality can feed into and influence the other. Finally, we proved our relation for discrete systems because a lot of these abstract results in quantum information theory have been proved for discrete systems. But you could extend our result to continuous systems, and it would be nice to find if there are any interesting situations in quantum field theory, maybe involving black holes, in which this entropic uncertainty relation would be as a useful application. In summary, we saw that two different types of physicists have two different notions of what it means for quantum operators to disagree. Pure quantum information theory involves uncertainty relations cast in terms of entropies. The intersection of condensed matter and high energy physics involves this notion of quantum information scrambling as measured by out-of-time ordered correlators. We managed to reconcile the two notions by proving an entropic uncertainty relation for quantum information scrambling. We can reason our way intuitively to the form of this relation. We saw how it behaves in numerical simulations and that it is experimentally testable. So, thank you for your time.
All right. Thank you, Nicole. Such a great talk. Let's move on to the questions that we have a few on the chat already. So one first question is, can you be more specific about the specific POVM that performs a weak measurement? And whether this is a fuzzy measurement with Gaussian noise, and furthermore, if there is an optimal choice of the measurement strength.
Yeah, so first, what is the form of the weak measurement Krauss operator? For those who don't have the quantum information theory background, these generalized measurements are cast in terms of Krauss operators. So in class, we usually learn about projective measurements in which depend essentially on, of course, projectors. So suppose that we have a state rho and we measure projectively, then we update the state by taking rho, sandwiching it between two projectors, and then normalizing the state. So when we turn to generalized measurements, positive operator valued measures, then what takes the place of these projectors is a Krauss operator, some K. So for the Krauss operator for the weak measurements looks like, I apologize that I don't have a notebook that I can also connect to the Zoom so that I could draw this out. So I'm going to explain it and hopefully it'll come across well enough without my writing. There is a square root of a probability, and I'll tell you in a moment what the probability means. So there's a square root of a probability times the identity operator plus a weak coupling times projector. So suppose that we wanted to measure the operator V weakly. Then the projector would be the projector onto an eigenspace of the operator V. And the weak coupling, it's not simply the little, well, let's say it depends on the detector's initial state and the outcome of the detector projection. So that's the weak coupling. And now let's step backward to the first term. I said that there's a square root of a probability. What is the probability? Well, suppose that you just prepare the detector and then measure it. You don't couple it to the system of interest. What is the probability that you'll get some outcome J? That is the probability in the first term. So the Krauss operator is labeled by this J, the outcome of the measurement of the detector. So that's what the Krauss operator looks like. What were the other parts of the question?
I guess that the other part of the question was kind of the role of the, the role of the measurement strength, right? Or I guess here is the coupling constraint. If there is an, I mean, you mentioned this weak coupling approximation that you do, but is there kind of an optimal value of the measurement strength, or that you could use to kind of see these effects?
There's a regime. So we, as I mentioned in our proof, Taylor approximated the log on the right-hand side of the uncertainty relation in the weak coupling strength. So we present there a condition that the weak coupling strength has to satisfy so that the Taylor approximation works. So that's one matter. And then, so once you've, so you just need for the coupling constant to satisfy that condition. Okay. So there is a range of values of G that can satisfy this condition. In our numerical simulations, we played with the possible values of G until we could observe an effect in the plots. And you can check the value in our paper. According, the numerical value that we chose won't really make sense. It makes sense only in the context of knowing what the other scales are, but I think that we found that 0.02 in our case worked well.
Okay, thanks. Another question here asked by Manuel is there any relation between the scrambling time and the time at which negative probabilities begin to appear in the Outoftime quasi-probability?
Oh, that's a great question. It is, well, let's see. This is something that we actually studied in a few papers. So let me go back to my PowerPoint and find the right slide. Apologies, it'll take a moment to find the right slide. Okay. And I'll share my screen again. Okay. We started looking into the negative values in this paper, which I said is like the biography of the out-of-time ordered correlator. And we found that in quite a lot of cases, the quasi-probability does acquire negative values. Then we looked more closely at the negative values in this paper. So the negative values do seem to be signatures of scrambling. And that actually we found can be useful experimentally. So suppose that you measure the out-of-time ordered correlator of some experimental system and you see the correlator drop. Then you might be very happy because your system has scrambled, it has interesting many-body entanglement. It turns out that the same observation would take place if your quantum system were simply decohering, so simply leaking out to its environment. So using the out-of-time ordered correlator alone, we can't distinguish scrambling from decoherence. But suppose that you measure also the out-of-time ordered correlator's quasi-probability, and you quantify how much negativity it has. If it has a decent amount of negativity, then according to our empirical results, you can safely conclude that your system is scrambling, and you can trust your out-of-time ordered correlator measurement. But if you see that the negativity, say that the system acquires some negativity and then it goes away, then you know that your system is decohering. You have to work on closing it harder before you can trust your out-of-time ordered correlator. So yes, the negative values seem wrapped up in scrambling and do appear at the scrambling time. A different question is, what's the significance of the imaginary values that we have? That is more of an open question.
Got it. All right, thank you. Let's see, we have a lot of people thanking you for a great talk and kind of giving a round of applause for the talk. And we have, I guess, one more question, which is about this Kirkwood-Dirac quasi-probability and whether you can, is there a relationship between the Kirkwood-Dirac quasi-probability and phase space?
Did you say n phase space?
Yes.
Yeah. So I showed you a an instance of a generalization of a Kirkwood-Dirac quasi-probability for a system of qubits. So it made sense to parameterize that distribution in terms of eigenvalues of the Pauli operators. But suppose that we are considering instead a continuous system, then it would make sense. And suppose that we are considering just a particle, not a quantum many-body system, then it would make sense to parameterize this distribution with position and momentum. In fact, when Kirkwood was first coming up with this distribution, he was literally thinking about phase space and saying, I want to be able to take a quantum system and get the classical limit of it. In the classical limits, we really will be dealing with a classical phase space. So what can I have that is on the way there for a quantum system, and what are the non-classical corrections and so on?
All right, cool.
I think I also have one more question.
Go ahead.
So you mentioned during your talk, there was a connection with the semi-classical interpretation of the Outoftime. Could you briefly elaborate on that? And does this also give you some semi-classical interpretation of your terms of order g squared in your final result?
Sure, let me get out the right slide.
People who are watching this later can always just fast forward.
Yes, good point. Okay, that's the right slide. So I'll share my screen. Here we go. Okay, here's one semi-classical story that helps us understand what the out-of-time ordered correlator has to do with chaos. In classical physics, chaos really hinges on sensitivity to initial conditions. So suppose that we have, for example, a double pendulum. We start it at some position and with some momentum, and we let it swing. Then it'll follow some trajectory in phase space. Now, suppose that instead we start off the double pendulum at a slightly different point in phase space and let it swing. It will follow a different trajectory, and these trajectories will diverge exponentially. We want to show that the out-of-time ordered correlator plays a similar role in a similar argument. So let's construct two protocols that also differ basically by an initial perturbation. First, we will start off with an initial state psi of our quantum many-body system. For the sake of this simple illustration, I'm going to focus on a pure state. Then suppose that we flick the lattice with some local operator v. And then we evolve the system in time, and we flick the lattice at the other end with an operator w. Then we are all-powerful experimentalists, so we reverse magnetic fields and so on, so that the system evolves in the reverse direction. So this final state I'll call psi prime. Now, suppose that we perform a very similar protocol that differs just in terms of what we do initially. So we have a state psi, and we omit the initial perturbation. We go straight to the time evolution. Then we flick on the left-hand side with w, and we reverse evolve the system, and now we perform our perturbation v. This results in a state that I'll call psi double prime. Suppose that we want to know how much that initial perturbation changes the resulting state. We might look at the overlap between the states. This overlap turns out to be the magnitude of the out-of-time ordered correlator. You can just plug from these equations into this one and find the out-of-time ordered correlator. Moreover, during a certain time period, this magnitude of the out-of-time ordered correlator changes in a way controlled by an exponential that itself is controlled by a Lyapunov type exponent. So this is a simple story that can help us understand how the out-of-time ordered correlator tells us something about chaos. So you also asked about the link to the quasi-probability distribution. So here, what's really evocative of this story is, let me get out the right slide, the set of measurements in the entropic uncertainty relation. So let me stop sharing my screen briefly so that I can find the right slide and go back. Here we go. We said that we found a generalized entropic uncertainty relation, then we had to find the right two measurements in order to get this entropic uncertainty relation to tell us something about scrambling. And it turned out that one measurement was a weak measurement of V followed by a strong measurement of WT, and the other measurement was the reverse process. This is a lot like what we do in the story that I just told when preparing psi prime. And this is a lot like what we do when preparing psi double prime. So the entropic uncertainty relation sort of strengthens the connection of the out-of-time ordered correlator to chaos, especially because chaos is defined in terms of tiny initial perturbations. And our measurement procedure really makes concrete what we mean by a tiny perturbation. The weak measurement of V needs to be weak. So it needs to be very close to the identity operator. And that, in that sense, technically, V is a small perturbation.
Okay, thanks. That clarifies a lot.
Great.
That's really cool. All right, I think that's it with the questions. And so thank you, Nicole, again for a fantastic talk and for joining us today. And thank you everyone for being there and attending this seminar. I'll just mention that next week we'll have another edition in which we'll we'll welcome Leah Santos from Shishio University, who will be talking about indicators of many-body quantum chaos and timescales for equilibration. And so we look forward to that and for another seminar next week. Thank you, everyone.
Thank you.